Hello everyone, I'm Norman Wildberger and welcome to 6. This is an elementary course in pure mathematics meant for a very general audience. While the main thrust of the course is very combinatorial and elementary, just dealing with points and combinations of them, in fact we're going to be touching base with a lot of other things. And naturally, there's some geometry involved because the nodes that we are sort of starting out with can be interpreted as points in the plane. And so geometry that has something to do with points in the plane will make a natural connection with the theory that we are exploring. That's the case here in today's video. We want to talk about this 3-4 bridge that we've already introduced and show how it plays an important role in a remarkable duality for conics. So this was discovered by one of ancient Greece's most important and influential geometers, Apollonius of Perga, who lived from around 240 to 190 BC. And he was one of the first to make a thorough investigation of these important curves called conics, including the ellipse, the parabola, the hyperbola, and also sometimes some degenerate cases like we've already seen, the line pairs that we were talking about. Now what he discovered was the following, that if you start with a conic, okay, so you have a conic in the plane, say this ellipse here, then that determines a correspondence between points and lines. For example, this point, capital A, ends up corresponding to this line, little a. And as you move the point capital A around, then the line little a will move around correspondingly. So how is that correspondence set up? Well, this is a preliminary guess. Here you see from the point A, the two tangent lines to the conic. So this green line is tangent to the conic and passes through A. And this is another tangent to the conic passing through A. And you can see that the line little a that we're saying is the dual of A is formed by the places where those tangents touch the conic. Over here, for this point here, for example, it's not so clear because this point D is sort of inside the conic and it's not so easy to draw tangents from the point to the conic. Nevertheless, Apollonius claims that there is a dual line right there. Now, for example, for a circle, there's another point, B. The dual line, little b, will be something like this. And in the special case, when the point is actually on the conic, then the corresponding dual line is the tangent to the conic. Now, this duality that Apollonius discovered actually plays a huge role in mathematics. And if you've seen any of my universal hyperbolic geometry lectures, then you'll know that it plays a huge role in the modern treatment of hyperbolic geometry done universally. Okay, so I want to explain the story here in the context of this 3-4 bridge that we've been discussing in our last video. So first, a little bit of notation. So suppose that we have a fixed conic C. Then Apollonius duality is going to pair points capital A and lines little a. So let's adopt this convention that points in this context are, say, given by capital letters and lines by smaller letters. Then the correspondence is such that we'll say that capital A is the pole or dual of little a. And we'll write that like this, that A, capital A, is little a with a little perpendicular sign. That's reflecting the relationship. And here is a picture that you can keep in mind. The conic happens to be a circle. There's the point A, and we're drawing tangents, and there's the line little a. So capital A is the pole or dual of the line little a. And if we want to look at it from the other way around, we'll say that the line little a is the polar or the dual of the point capital A. And we'll write that as little a is capital A with a perp subscript, and we'll say A is A dual. Okay, so that's the notation that we're going to be using. So pole and polar are kind of traditional, but I find it's useful actually just to use the word dual to express this relationship. It's very much a duality. Okay, but what is the relation exactly? How do we define this correspondence between points and lines with respect to a conic? All right, so here is the construction of the duality of Apollonius. So we'll start by a point, capital A, and we'll explain how to get the polar or the dual, little a, of the point. And it's all with respect to a conic C. So we're assuming that there is a fixed conic which we can see in the plane. So the first step is to take our point A, okay, and draw two lines through A which each meet the conic C at 2 points. So in this case, the two lines are the ones in black. This one here and this one here. These are two lines which are passing through A and which do indeed meet the conic. This line here meets the conic at 2 points, which we'll call 1 and 2. And this line here meets the conic in 2 points, which we'll call 3 and 4. So we've started with a point A, and then we've chosen two lines, and now we have obtained these 4 points forming a quadrangle on the conic. Now what we do, we construct the diagonal triangle ABC of this quadrangle 1, 2, 3, 4. We now go back to our 3, 4 bridge, and we say, aha, we have 4 points forming a quadrangle in the plane. So with those 4 points, we can make this 3, 4 bridge construction of finding the diagonal triangle. How do we do that? Well, we just connect the 4 points in all possible ways with lines. There are 6 lines altogether that we can draw between 4 points. But 2 of them we already have. The 2 black ones we've already got because we started the construction with them. So there are 4 additional lines that we can draw between these 4 points. So we can draw, for example, 1, 4 in green, 1, 3 in green, 2, 3 in green, and 2, 4 in green. Well, then what happens is that those 4 green lines will meet in some additional points. The line 1, 3 and the line 2, 4 will meet in an additional point, which we're calling C. And the line 1, 4 and the line 2, 3 will meet in an additional point down here, which we're calling B. The original 2 lines that we started with, well, they're already intersecting in the original point A, which is how we started the construction. Okay, but now we're getting 2 more points, B and C, as the meets of these pairs of new edges formed by the 4 points. Okay, and now what we do is we set little a, the dual of capital A, to be the line BC. We started with A, constructed 1, 2, 3, 4 this quadrangle, did the diagonal triangle construction, found B and C, and now we join B and C and we define this line to be the dual of the point A. We start with A, we use the conic to create this line here. That's the dual line of the point A. That's Apollonius' construction. Now, if you've been watching very carefully to that last slide, you may realize that there is a slight problem, kind of a logical point which we have not yet addressed. And there's a magical fact that rears its head now to resolve this issue. So what is the issue? So the point is that we started with this point A and the conic, and we chose these 2 lines through A that meet the conic. And then we did some construction starting from that. But how do we know that what we end up with doesn't depend on the choice of the 2 lines through A? So for example, here's same kind of picture. I have the circle, same as I did in the previous one, and the point A is in the same relative position. But now I actually am choosing two different lines through A. And the diagonal points that we get in this case are up here. C is now up here, and B is down here. Those are quite different positions than we saw in the last one. But nevertheless, the line BC that they determine seems to be in exactly the same position as the line BC that we obtained in the previous slide. And this is the magical fact. The magical fact is that the construction of A, the dual of A, point A, is independent of the choice of two lines through capital A. So this is a remarkable fact. This is a non-obvious and somewhat remarkable fact that makes the construction work. So if we don't know this, then we are legitimately able to say, well, wait a minute, this construction is not a valid construction because it depends on certain choices that you've made. So it's this fact which sort of forms the logical basis for the Apollonius duality. Now, as an interesting consequence of that, we actually can look at this situation and see that there's a pleasant symmetry, because we have these 3 points A, B, and C. And we've just shown that this line here, the line BC, is the dual of A. But if we stare at it for a second, we see that, in fact, also the dual of this point B is the line AC. I want to show you that. So suppose that we're having the same diagram, but now we're interested in the question, what is the dual, or the polar, of the point B? So what do we need to do? We need to choose two lines that pass through B and that also meet the conic. Well, the two lines that we can choose are these ones. We can choose this line and this line. If we do that, then the 4 points that we get are exactly the same as the 4 points that we got when we were working with A. And so the diagonal lines that we have to create are already on this picture. So we have to create new lines. This and this will meet at C. But we also have to create now these two lines, which are new from the point of view of the construction here, which will meet at A. And that means that the Apollonius construction is telling us that this line, AC, is actually also the dual of the point B. And exactly the same argument, let me go over it again just to reinforce it. The same argument shows that if we're interested in the dual of this point, capital C up here, it's going to be this line AB. So for example, if we, how do we see that? If we start with C and we choose the two lines to be these two here, then the points of meeting with the conic are the 4 points, 1, 2, 3, 4, that we've already been talking about. And then the additional lines that we need to construct are these two here, which meet at B, and these two here, which meet at A. So yes, indeed, then we need to join A and B to get the dual of C. Notice that this is already telling us something geometrical, because if this is the dual of C, then the tangent to C, to the conic, those two tangents will actually meet at these 2 points where that line AB meet the conic. And similarly for B, the tangents will be the points where this dual line here meets the conic. So we get actually a very nice threefold symmetry here. Okay, so this triangle ABC, I guess ABC in this order, this has a very pleasant property that with respect to the conic that we're starting with, the conic C, which is a circle in this case, this is a self-polar triangle. What does that mean? It means that the dual of A is BC, the dual of B is AC, and the dual of C is AB. Exactly this configuration plays a very big role in the universal hyperbolic geometry course, which I hope some of you who are a little bit more interested in delving into geometry will look into. Okay, so it turns out that this duality is exactly perpendicularity in the hyperbolic setting. And so what we end up having is a triangle here, which has perpendicular sides. So that these two are perpendicular, and these two are perpendicular, and these two are perpendicular. Very interesting story. So very directly related to this geometry. So you can see that what we're talking about here is not some kind of esoteric thing. It's an aspect of mathematical reality which is really very, very fundamental. And this has been known for thousands of years. Apollonius, 2,500 years ago, he was interested in this. Okay, this is really a fundamental thing, and it's something, unfortunately, that even undergraduates go through their entire career and they don't learn this. Okay, so we really ought to think again about mathematics education in the modern world. Okay, and I'm hoping that this course will provide something of a roadmap for ways of thinking about mathematics which are more elementary, but still touching base with really fundamental things. So let me talk a little bit more about conics, which are very central objects in mathematics. Very, very central. So the ancient Greeks thought about conics as being something that you get when you kind of put lines and circles together. So if you start with a circle and a point in three-dimensional space, which is not on the circle, and you join the given point with the points on the circle, you get a cone. Okay, and so they thought of a cone as some kind of sort of three-dimensional version or extension of a circle. And then these conic sections were slices of a cone. So you take a cone like this and then you slice it with planes and you get the conic sections. That was Apollonius' original point of view towards what a conic was. So for example, here's a cone in red. Maybe think of this as the top, although it actually is supposed to extend beyond, but let's suppose that this is sort of the top temporarily. And here's sort of the vertex. We're looking at all the lines that pass through the vertex and points on this circle. And it has a two-sided aspect, so there's a bottom because these are actual lines that go indefinitely in either direction. Okay, and then if we slice this thing with various things, we get certain curves. So if we slice it with the plane right up at the top, well, we'll get that circle that we started with. But if we slice with a plane at some kind of angle like that, then we're going to get an ellipse. And if we slice, say, with a plane which actually is parallel to one of the lines of the cone, so if we take that particular line of the cone and take a plane which is parallel to it, meaning that this line actually would actually lie on the plane, and you slice the cone with such a plane, then it's only going to meet one of the two naps of the cone, one of the two sort of parts of the cone, and the curve that you get is a parabola. On the other hand, if you take a plane which is sort of at a more arbitrary position and happens to slice both the top and the bottom part of the cone, then it's going to slice out a curve which has two components, a component up in the top one and a component in the bottom one, and that's a hyperbola. Okay, so that's how Apollonius thought about the different kinds of conics, and that they're all essentially generated from a cone. Now, this is a very powerful way of thinking because it implicitly introduces ideas of projective geometry, that if we're looking at one of these curves, okay, from the vertex, so imagine putting your eye at the vertex and you're looking up at this cone, okay, and maybe someone has drawn in this ellipse in blue, or maybe somebody else has drawn in this circle in red above it, okay. As far as you're concerned, they're kind of overlapping. Yeah, they're overlapping. So if we make some construction on the circle, exactly like the kind of construction that we've just been doing with maybe 4 points, and then you draw some diagonals and you draw some more things, okay, then that construction, if you're looking at it from the vertex, can be thought of as actually also construction in the plane of this ellipse. So in other words, you can use the fact that if your construction only involves points and lines, then using this perspectivity, you can kind of transfer facts about one of these diagrams to other diagrams. In particular, if something is working for the circle along the lines of what I've been showing you, then it's also going to be working on an ellipse if you just take the corresponding diagram. And it doesn't have to be an ellipse, it could also be the parabola or the hyperbola. The same kind of argument shows. So roughly this is a kind of a projective view of sort of explaining why we shouldn't be too surprised if constructions which only involve straight edges and points, joining points to form lines and meeting lines to form points, if those constructions are extending from circles to ellipses to parabolas to hyperbolas. Okay. Of course, this is quite a different viewpoint from the point of view of conics that I described in an earlier lecture when I told you that in the 17th century, with the introduction of analytic geometry, conics were understood by Descartes and Fermat as essentially quadratic equations in x and y. Okay, so it's quite a remarkable thing that this geometrical orientation of Apollonius ends up being essentially the same as the algebraic representation of Descartes involving quadratic functions of x and y. So for your homework, this is what I want you to do. I want you to explore a little bit the geometrical construction that I've shown you of Apollonius. And I want you to convince yourself that it actually works by actually investigating it concretely and explicitly. And to do that, we're going to use a dynamic geometry package called GeoGebra, okay, which is freely available and very popular in lots of circles, especially educational circles. So you can download GeoGebra onto your laptop. In fact, there's also a browser version, so you can just do it on your browser. And you can make an exploration, and I want you to empirically verify the magical fact. So that involves, first of all, cooking up a conic section. And how do you cook up a conic section? Well, there's a kind of a third way of thinking about a conic section, which we're going to talk about more, but it relies on the following crucial fact, that 5 points actually make a conic. If you have 5 points sort of randomly distributed in the plane, then there's a unique conic which passes through those 5 points. So the symbol for GeoGebra actually illustrates this idea. That's what it looks like there. So if you draw 5 points on the plane, then there's a special tool that has a shape like that you can click on, and then you click on the 5 points and boom, it will give you the conic. And it may not necessarily be an ellipse. It may be a hyperbola, depending on the position of the 5 points. So I want you to experiment with this. I want you to convince yourself that this is happening no matter what conic section that we start with. So you choose your 5 points, then you have a conic, and that's the fixed conic there. And now we want to investigate the duality construction. So what I want you to do is to choose some point, A, so you create a point, and then that will be movable. Just draw A. There's a movable point, A. And then we're going to do the construction. So you want to find 2 lines that meet the conic. And how you're going to do that is the following. So what you want to do is you want to choose 2 points on the conic. So you can create points on the conic. And I suggest that you use 2 different points, not one of the 5 that you already have. Okay? And then you use one of these points connected with A. Okay? You get a line. And then that line is going to meet the conic in a second point. Similarly, the line through A and this other point in green is going to give you a second point up here, let's say. And now you have 4 points on the conic. Now you're in a happy position. You can draw the diagonal triangle and determine where the dual line A dual is. And once you've done that, you can verify the magical fact by dragging these points, right? If you drag that point, move it up and down the conic, then things are going to change. But hopefully that dual line that you've constructed is not going to change. The actual position of the dual line is not going to change. So you'll be able to empirically verify that the fact is true, even if you still don't really know why it's true. So this is an elementary course, so I don't expect us to understand everything, okay? I do want us to have a clear idea of what the logical structure is. So we're on a major path, okay, and I want to be precise on that major path. But every so often there will be, little sightseeing tours, like I'm giving you here now, okay? And I'm going to tell you about something. It will not be necessary logically for you to understand why this magical fact is true. I hope that you're curious and you might, wonder, why is that actually true? Can I prove that? But that's a little bit challenging. And we don't actually have to do this at this stage here because we're not using this magical fact in an essential way in our development of 6. Okay? We're just using it to illustrate the landscape that's adjacent to what we're exploring. So even if we don't know how to prove something, we can still verify it. We can still make calculations or constructions that reinforce our faith in the statement, even if we may not have an ironclad proof of it. Okay, so that's something very positive that I want you to think about, of being able to feel that something is true because you've checked it out in lots of different special cases. Okay, so you have kind of some confidence. Maybe you don't have 100% confidence, but that's all right. All right. So we've touched base with some interesting geometry, which may appear to be somewhat tangential to the main thrust of the course, which is combinatorial, but you never know. You never know which way mathematics is going to go. Maybe the kinds of things that we're going to be doing will come back and connect more and more with geometrical kinds of things like we've introduced today. I'm Norman Wahlberger. Thanks for listening.